Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to take a look at expressions and equations and take a walk through algebra all the way through calculus. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI Technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. Tonight I'm excited to be joined by our two panelists, Janice Michener and Dennis Wilson. Janice has been a mathematics teacher for over 35 years, teaching courses from Algebra 1 up through Calculus 3. She received the Presidential Award for Excellence in Science and Mathematics Teaching, is an AP Calculus reader, and has been with the T-Cubed organization since 2003. Her passion is mentoring and training teachers on using technology as a tool to enhance learning. Janice, thanks so much for joining us.
Hello, I'm excited to be here tonight.
And for the last 23 years, Dennis has been teaching at Landmark Christian School in Fairburn, Georgia. Dennis is passionate about teaching with technology to help his students learn math through the use of multiple representations. He has served as an AP reader for calculus for the past 4 years and is currently serving as the president of the Georgia Association of Advanced Placement Math Teachers. Dennis, so great to have you with us tonight.
Thanks, Mike. I'm excited to be here, and hello to everyone, and welcome.
We're expecting a large crowd, so your audio is muted. Feel free at any time to send questions to Janice or Dennis using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, this session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. We hope you don't have any audio issues tonight, but in the event that you do, try selecting Communicate from the very top of the WebEx menu and choose Audio Broadcast. At this point, Dennis is going to discuss our agenda.
Thanks, Mike. So we're in the middle of our welcome and introductions, and in a minute, my partner Jan is going to discuss our expected outcomes for the evening. While we go through through our agenda tonight, we will start with discussing the mathematical practices from the new course and exam description for AP Calculus. And while this is certainly geared towards calculus, we are starting in algebra, and most of it will be geared for algebra teachers preparing students for AP Calculus. We'll be looking at equivalent expressions using absolute value, logarithms, radicals, and how to use technology to explore that. We'll look at equivalent linear equations and rational expressions, and we will provide technology tools that teachers can provide their students with to explore equivalent expressions. And then at the end, I hope all of you stick around for the very end, because we'll have a webinar drawing where the winner will receive a free registration to T-Cubed International Conference in Dallas, Texas this March upcoming. And it's a wonderful conference. It's my favorite conference of the year, and I hope to see you there.
Thanks, Dennis. And Janice is going to talk about our expected outcomes.
So tonight we're going to discuss what it means for two expressions to be equivalent. We're going to demonstrate how technology can be used to explore whether two expressions can be equivalent, as well as identifying the AP Calculus mathematical practices as stated, as Dennis said, in the course and exam description. And this is very useful in using these ideas in vertical alignment of algebra through calculus curriculum concerning equivalent expressions.
Thanks, Janice. Dennis, you should have control. Feel free to share your screen.
Okay. Thank you, Mike. So this year, the AP Calculus, the College Board came out with a new course and exam description for AP Calculus. And while it's a new course and exam description, the course content is the same and the exam is the same. Some of the ideas in the structure have changed, and one of the big changes is the College Board has gone from mathematical practices for AP Calculus to a set of just mathematical practices, believing that these are practices that students should be learning to practice as soon as they enter algebra and go forward through the curriculum. There are 4 mathematical practices as described by the course and exam description. The first one is implementing mathematical processes. The next one is connecting representations. The next is justification. And then the fourth is communication and notation. Jan and I will be looking at some specific skills that are related to equivalent expressions and equations tonight. Specifically, under connecting representations, we'll look at identifying a re-expression of mathematical information presented in a given representation. Under justification, how to apply technology to develop claims and conjectures. And under communication and notation, we'll be looking at how to use precise mathematical language and to apply appropriate graphical techniques. So as we get started, I just kind of want to discuss what is equivalence. Students from a very young age start talking about things that are equivalent. In kindergarten or maybe first grade, they first encounter equivalent sums. 5 equals 2 plus 3 equals 5 plus 4. And students are taught that these things are equal, and they're given visual representations of what that might mean. They might have 5 objects, and those 5 objects can be regrouped to a set of 2 and 3, but I still have the same total number of objects, or if I regroup them into a group of 4 and 1, I still have that same total. And students understand that equal signs means that the quantity is the same on either side. As they proceed through elementary school, they might come into equivalent ratios in 4th or 5th grade. What does it mean for 3/5 to equal 15/25 to equal 6/10? Students are taught to understand that those are same places on a number line, but again, they're given visual representations. 3/5 of a whole might equal 15/25 of a whole, would equal 6/10 of a whole. But once they leave arithmetic behind, equivalence takes on a new meaning. So we have here an expression, 3x minus 4 equals 8. And so what does that expression mean to a student? Up until they started algebra, they've always seen equal signs to mean that two sides are always equal. But in this expression, 3x minus 4 equals 8, it's only true for a particular value of x. And students change their mind about what does an equation mean? What does it mean for two things to be equivalent? And then they forget sometimes that two things can be equivalent for all values. I asked my students in Calc 3 just this week, for what values of x would this expression be true? And you should have heard them debate. Well, we have two parabolas and they're both opening upward, so are they going to cross once? They might cross twice. What does it depend on? Until one student finally said, oh, those two sides are just expressions. And they realize that sometimes when we have an equation with equivalent expressions, it's true for all values of the variable. So what we're going to look tonight at is how can we help students to understand when things are equivalent, because they might come into equivalent equations. We have 3 types of equivalent equations. We have the point-slope form, we have slope-intercept form, we have standard form. And from each of these, an algebra teacher might want students to glean different information about the set of x and y that are related in these equations. How can we prepare students in order to understand what information is going to come from these equations? So here's this particular sample SAT style question. We have the standard equation, 2x minus 3y equals 6. And students are being asked which of the following is an equivalent equation form of this equation. True, a student could go ahead and solve for y and get one of the forms below, but let's explore how we can help a student understand what information can come from standard form. So I'm going to start on the TI-Nspire first, and then I'll move to the TI-84 and show how we could do it there. So I'm just in a new document on the TI-Nspire, and I am going to add a graphs page, number 2. And instead of entering in my expression in function notation, I'm going to type a type my equation as a relation. There's various ways to do this. I could use the menu and change graph entry edit by choosing number 3 and choosing relation. But my favorite way to choose the relation is just to go ahead and to delete the equal sign, and I'm given the chance of multiple options, and number 6 is relation. So I'm going to type in the expression for the standard form of the linear equation. I've got a times x, and here on the Nspire I have to be careful, because if I type just ax, multiplication won't be implied there. The Nspire will think ax is its own variable. So by typing a times x, the Nspire knows I'm talking about the product of two variables, plus b times y equals c. And when I press enter, it asks me, do I want to create sliders? So now I have 3 parameters, a, b, and c, for which their values can be changed dynamically, and I can watch the change right there on the graph as it happens. So I'll hit enter for OK. I have 3 sliders that can be moved as I want, and I have the graph of my equation. So right now, first thing I'm going to do is I'm just going to grab this equation and move it up so we can see it up in the corner. And you might notice that right now the equation is exactly as I'd entered it. A times x plus b times y equals c. Well, there's a new feature on the Nspire CX2 that allows me to change this label so those values from the slider a, b, and c are dynamically updated. So I'm going to do that now. I'm going to move my cursor over the graph of the equation, and I'm going to hit Control Menu. Control Menu gives me a context menu, and I'm going to choose number 3 here, Attributes. When I hit Attributes, I can change in Attributes. I could change the thickness of my plot by going left or right. I can move down and change whether my plot is dotted, dashed, or continuous. And if I move down a third time, it says Label Parameters, Show Names. Right now it's showing the names A, B, and C, but if I move to the right, now those values will be shown in my equation. I have graphed x plus y equals 1. So once we have this, what are some of the ways, what is some of the information we would want students to glean by a quick glance at an equation in standard form? Just take a few seconds for yourself and think about what those might be. So one thing I want my students to be able to understand is, what does each parameter, A, B, and C, how does that affect the equation? So I might ask a student, changing A, what will change in the graph of my equation? Well, changing the value of A, that coefficient of x, will change the slope, and it will change the x-intercept. But as I change A, I will also see something remains unchanged, and that is the y-intercept. A has no effect on the y-intercept. And we might ask our students, why does A have no effect on the y-intercept? And point to the fact that x is 0 on the y-intercept, and so it's that A value will be multiplied by 0 and have no effect. I might change C and see what happens there. Well, here, both intercepts change, but the slope is unchanged by C. Or I might change B and notice that the x-intercept is unchanged. Or I could ask my students, for what conditions of A, B, and C would the slope of the line be positive, and for what would they be negative? Now, typically standard form is just a positive value of A, and so I'll just change B, and notice that when A and B are both positive, I have a negative slope. And when A and B are opposite signs, I have a positive slope. I might ask, for what conditions will the graph go through the origin? I can move it, and I can see that as it goes through the origin at C. And so there are a lot of ways to dynamically explore what a standard form of the equation does without requiring a student to repetitively solve that equation into y-intercept form and into slope-intercept form, and to sketch each one on the paper. It's dynamically updated, and we can explore the changing parameters. We have the ability to do the same thing on the TI-84. I'm sorry, my TI-84 software has gone off. I'm going to load it real quick. But as we come back to this expression, one of the things I would also recommend is on your graph, if you go to Menu, View, you can show a grid with number 6 and show the line grid. I think students benefit from being able to see a line grid on their paper because it helps them to understand what the slope values are, because they can see where the line hits at those integer points. And so from this line with the grid on, they can see that it goes up 1 and over 2, and they can see that the slope is 1/2. Okay, so I'll be starting with the TI-84. The emulator's been cleared. It's almost like resetting your RAM. And all I'm going to do first is I am going to change my window before I ever put in anything into y equals. I have a favorite window on the TI-84, okay, and it's not the zoom standard. So what I'm going to do is I'm going to press zoom 4 for zoom decimal. And it will show me this window, and while I'm at it, I think what I will also do is I'll put that grid on that I just showed for the Nspire. So I'll press second, format, and I'll go down and turn on the grid line. And while I'm at it, I'm also going to go down and turn expressions off. So now if I were to look at the graph, I've got a grid and it's square. That's one reason I like zoom decimal. And second, I've got the grid on, and when I graph my equation, I will have no expression at top. The next thing I'm going to do is I'm going to press the apps key. Here we're going to make use of the transformation app. So when you use a menu on the 84, and the list is really long, what's nice is I can go up from the top and through the bottom and hit transform. So I'll hit enter for transform, and I will get the screen that gives me some instructions. Well, we won't be using animated graphing, so we won't need to deal with the X resolution, but it's set by 1 for default. If I wanted to animate some of the parameters, I should set that X resolution to 3. But I'll press enter, and I'm going to go to Y equals. You can see that this screen's a little bit different now in terms of the icons that are next to Y1 and Y2. These two functions now allow for the parameters A, B, C, and D to be entered and manipulated live in the graph. So I'm going to enter the equation here, negative, and then I want the fraction A over B. So I'm going to use a shortcut to get the nice horizontal fraction bar, alpha x, and I'm going to put alpha A in the numerator. Then I'm going to put alpha b in the denominator. There's my fraction, times x, plus, and then I'm going to press alpha x again to get my fraction bar, and I'm going to do alpha c divided by alpha b. And so now when I graph, I have a very similar situation. While I can't see the equation dynamically updated like I could on the Nspire, I can still make changes to the value of A, B, or C as I want. If I press up and down, it moves between the different values that I might want to change. If I move left or right, the values of A can be changed, and I can once again see that when I change A, there is no change on the y-intercept, but the slope and the x-intercept change. I can move to C and see that the slope doesn't change when I change the value of C. And I can also go and change B and see that when the two signs are negative, I'll have a positive slope, but when the signs are the same sign, I'll have a negative slope. This idea is powerful in putting it in the student's hands, and what's nice, while we entered an equation that the student might not have understood at the beginning, they can start to understand why negative A over B sits there in front of the x as we connect this representation to point slope. As we move on, let's go back to this AP question, and we can see real quick that instead of doing the algebra, because not all students are quick at algebra manipulation and can't do it in their head, hopefully if we've drawn connections, students can quickly see that x and y are different signs. If x and y are different signs, we are looking for a line with positive slope, and so choices A and D are gone. Now I just have to pick between B and C, and a quick look at what the y-intercept is, that is when x is 0, will show me that it's +2. And so a student has a quick way to answer an SAT question, not from their skills in algebraic manipulation that might take some time, but through their understanding of the from their understanding of the standard form of the equation of a line. These ideas can then be expanded to perhaps you could create a document that would explore the values of A, B, and C in the standard form of a quadratic equation and how they compare to the vertex form of the quadratic. Here, students might learn that this value of B, opposite of B over 2A, as my students come in knowing, would be the vertex. So they're looking for a -3, and so A and C might be the choice, but which one? Well, if they understand vertex form, they'll know that these parabolas open upward, and that the lowest point on this would either be -1 or -17. But the y-intercept in standard form is -8. If the y-intercept is -8, then -1 certainly can't be the vertex, and so they know that the choice is A. This is an important skill that students can look at 4 choices and eliminate the 2 wrong answers. And it pays dividends when they get to AP Calculus, when they're asked to identify a re-expression of mathematical information presented in a given representation. So perhaps the representations are 2 algebraic formulations. They might be asked to find the derivative of a quotient of a rational expression using the quotient rule. I always tell my students that once they're in calculus, no longer is their goal algebraic simplification, but algebraic recognition. They can make very quick work using the quotient rule and get this expression. But what their job is on a multiple choice question is then to take that expression and connect it to one of the answers. What's nice about the AP exam is there are 1 right answer, but the other 3 wrong answers, the foils, are built upon calculus errors. And so usually a good calculus student who did calculus right can identify which one to choose. A quick glance at all 4 of these choices and we can see that the quadratic term is different in each of them. All I would have to do is evaluate which quadratic term would work here, and I would have the answer. And so looking at 2x squared minus 4x squared, I would know that A is the right answer. And so at this time, I'm now going to pass it back to Jan so that she can talk to us about, how students can determine if 2 expressions are equivalent for various values of x. I need to find one thing. I'm sorry. Okay. Jan, it's your go.
Okay. And I need to share my screen. Okay. Dennis, is this looking good?
This is looking good, Jan.
Okay. All right. So the mathematical practices that I'm going to be covering, Dennis has gone through them in detail. So basically, I'm going to be doing skill. It's called a skill 2.C, identifying a re-expression of mathematical information presented in a given representation, as well as this justification, skill 3.1, applying technology to develop claims and conjectures. Now, keep in mind, this is not assessed. That I feel that applying technology helps students to kind of drill that property into their brain so they can help recall it maybe later on and kind of give them just ways to explore concepts. Okay, so I am going to start with logarithms. Okay, what I have here, and I supplied this activity for you, I have a little snippet of an activity here where I have a bunch of statements for students to look at and decide, are these statements true or false? So I'm going to look at the left side, I'm going to look at the right side. And, you know, just real quick, do we think it's true or false? What technology did you use to come up with this conclusion? Or what did you use to come up with the conclusion? And can you come up with a different method to also come up with this conclusion? So getting them to think different ways. If it is it true for all values of X? And if it is true, can you write a general rule? And are there any domain restrictions? Now, when I look at this little snippet, there's two ways you can use this. If you use something like this for the first time that students see logarithms, I would probably have quite a few more statements here, very similar, getting students to identify, are these true or false? If you're using this just to review, like maybe in pre-calculus or in calculus, their log properties, I might not need as many statements here for students to identify the properties that they are using. Okay, so what I'm going to do here is with each of these different expressions, whether it be logarithms or equivalent expressions, whether it be logarithms, radicals, or even trig identities, I'm going to highlight different features of the calculators that can be used, both the Nspire and the 84. The technology skill featured will be used as a tool to help students explore, and that's our goal for the evening is, can we get these students to explore our equivalent expressions that we're looking at? Now, remember, before we go too much further, the two expressions are equivalent if they give the same solution for every X. And we really need to look closely at each expression's domain to find the values at which those two expressions are the same. Okay, so in looking at these expressions, I'm going to look at the bottom one, number 7, log base 3. And I'm going to start with the 84, log base 3 of X divided by 4. So let's bring up my 84. Okay, now one thing I do need to kind of mention is a lot of times in my actions, I like to reset my emulator, and I say, yes, reset. And I want to kind of keep you aware of the fact that all values for the variables are set back to 0. So keep that in mind as we do this problem. I would like to also mention of our statement that we're going to look at, I think it's very helpful to have students type in the left side and the right side of the expression into a y equals so that I don't have to retype it over and over and over again. All right, so where can I do log base 5 on, or log base 3 on an 84? I'm going to hit alpha, window, and if you look at number 5, I have log base. So yes, we can do more than just log base 10 or base E. So I have log base 3, and I'm going to type this in as I go. Fraction alpha x, that's my nice little fast fraction, and I have just x divided by 4. And I'm going to hit enter. And then over here, I'm going to type the right side of that expression, which was log, again, alpha, window. I choose number 5, log base 3. And we're thinking, I think the one that I gave them was probably a true statement. Log base 3 of x minus number 5, log base 3 of 4. Okay, so one of the ways that we can look at this, and again, I've typed these in here so I can type them quickly, is I'm going to go to a calculator screen, get off the y equals, and I'm going to have the calculator test this for me. So I'm going to hit alpha trace to get all the functions to come up here, and I have my y1, and I want to know, is this equal to? So I'm going to hit my test button, which is above the math, second math. I hit my equals, and I want to know, is that equal to y2? Alpha trace again. I'm going to go to y2 and hit enter, and notice it says error domain. And, you know, students may look at that and say, wait a minute, I think that's a true statement. So I have them graph it. And before I have them graph it, when I'm looking at equivalent expressions, I want to go over here and I want to make sure that the attribute, I want to change that line. So I'm going to hit enter there. And the line that I want to pick is not just that solid line. I want to pick it looks like a circle with a tail. It's a path tool so that I can see that it's graphing on top of that, one on top of the other, if it's true. Oh, look, it is true. Okay, and I'm going to use Dennis's suggestion. He likes doing that zoom 4. You see a little bit more of your graph there. And yes, it does look equivalent. So the students may say, well, why, when I did my, on my home screen, why was that coming up as an error? Well, if they were go to it now and hit enter, it comes up with a 1, which means that's a true statement. And what the calculator, the 84, does is it will, when it's evaluating a test function here, it will only test one number. And it will test the last X value I think that it had here. So it's testing that one number, and yes, it is true. Okay. So the other thing that I like to look at is when you're graphing these, let's go back to this graph screen, it graphs the domain at which those two statements are true, or the two expressions are true. So that statement is true for this domain. The other thing that I like to look at on the 84, this is kind of an interesting idea, is I want to come down here to my Y3, and I'm going to once again change the color because I like bright colors. So I'm going to hit enter here, and I'm going to graph this one in magenta. And again, I'm going to change my line to be that path tool. And I'm going to graph when is my Y1. So I'm going to hit second. No, I'm not. Alpha trace. When is my Y1 equal to my Y2? Okay, now, I also want to kind of make sure that I have my other two equations shut off right here. Okay. Now this will be interesting. So I'm asking it to graph when is Y1 equal to Y2, and so I always, have students do that, and they look at that and they're like, it's graphing when Y is equal to 1. Well, what is that telling us? Well, this is saying these are the true values. Of all these X values, that statement is true. So let's go up and let's look at one that's maybe not true. So I'm going to insert, instead of retyping everything, second delete is insert. I'm going to make that the opposite of log base 3 of x. Now notice since I went through and changed it, it's turned back on. So I'm going to shut it back off. And I'm going to come down here and I'm going to graph it again. Oh, notice that I'm graphing y equal to 0, which means it's false, but did you see this little pink dot show up here? Maybe magenta was not the best color to pick to be able to see that on everybody's screen. But I would ask students, what is happening right there? Looks like a x equal to 1. Well, let's go back and maybe turn those back on and see, see actually what's happening there. So when I hit graph, what's happening to my y1 and my y2, well, look right here, at x equal to 1, they intersect. So at that value, that one value, that statement is true. But for every other value, they were false. Okay. I think that was all I wanted to do on the 84. So let's switch over to the Nspire. On the Nspire, we do the same thing. I always like to work in documents, so I'm going to start a new document. And I'm going to add a graph. And again, I'm going to type in the left side and the right side of this statement. So where are log base other than 10 and E located at? I'm going to hit Control 10 to the X power. That template already has the base there. And if you don't put anything there, it'll assume it's base 10. Where's the fraction key? Control division. And I have x over 4. And then I'm going to hit tab to get that screen to come back up so I can do my right side, which again is my log base 3 of x minus log base 3 of 4. Okay, and again, if you notice here, we have, I'm trying to get these, both of the functions right here on top of each other. I'm trying to move one up. Here we go. So we can see both of them. Now, what I like to do on this to be able to see what's really happening here is I'm going to hit Menu, and I'm going to hit Trace, and I like doing a trace all. So when I start arrowing to the right, look down there on the right-hand corner of the screen, I actually have my points being evaluated at the same x value for both functions, and I can see as I glide around over there, I'm getting the same values for F1 and F2. And again, it's only graphing the x values at which this statement is true, because there's that asymptote. We cannot do, look right here, I can't use 0. There's no points. Come over here to the negative value. There's no points there. So even though I'm, students may argue that it's crossing over that y-axis, we can look at that and say, it's not quite doing that. Okay? So let's go back here to my slides and let's look at this. So there's just a little snippet again of how you can have students look at that. And where does this come in handy in calculus? Well, with calculus, we have to take the derivative, or we do take the derivative of natural logs. And that expression on the left side, I really have no desire to take a derivative of a log with a quotient rule. I would much rather expand that logarithm and use those logarithm properties to make it easier to find those derivatives. So again, having students in levels like pre-calculus and Algebra 2, working with their technology and kind of exploring these properties, I think is just very helpful to help them remember these equivalent expressions. All right, switching over to absolute values. When I'm looking at absolute values, again, I'm thinking about upper elementary school and into middle school, where students just take like the absolute value of 2. They know it's going to be 2. Or the absolute value of -2. And they're like, well, it always has to be positive. So my answer is 2. And then we kind of advance to the next level where we bring in variables. So students are kind of thinking, well, inside the absolute value has to just be positive or negative. So they may look at this and say the absolute value of u could be u or the opposite of u. And then they go one step further, maybe the next level up, and they're thinking, well, if I have the absolute value of 2x plus 3, that, using my patterns that I'm seeing here, should be the same as 2x plus 3 and the opposite of 2x plus 3. And so I always ask my students, are you sure? All right, so let's start with the 84 and let's kind of go exploring. And again, I'm going to go to Actions, reset my emulator. Yes, I want to reset it. Okay, so let's go to y equals, and let's go to the absolute value. So absolute value here is alpha window, number 1, and we are doing 2x plus 3. And then I ask students to go ahead and put in what the two equivalent expressions are that you gave me, 2x plus 3 and the opposite of 2x plus 3. So kind of thinking about this in a piecewise fashion. Okay, now I think what I'm also going to do is change up some things here. Okay, so here I'm going to go back over here and change my line to that path tool. And again, I like to graph with lots of color, so I'm going to hit enter. And I'm going to choose a different color. I'm going to choose green this time, again, with the path tool. Okay. All right, so if I look at that, oh, one other thing. Let's try something new here. Let's go to mode. It's not new. What am I thinking? It's just kind of out of the ordinary. Instead of graphing sequential, let's graph simultaneous. That just means I want everything being graphed at the same time. Okay, do I have everything set up the way I want it? Maybe not. I want to do zoom 4. I should have probably typed that in first. Oh, wait a minute. Look what's happening here. If I notice okay, let's go back. What is this blue line? Oh, I have to finish graphing to go back. Well, my absolute value, I'm pretty sure, is my blue line, because look, it's coming back up here. And notice the red line is down here by itself. Oh, it's not matching up with my blue line at all. But I've got this green line that's matching up. That green line was the opposite of 2x plus 3. So that matches up with my blue line until I get to this minimum value. And then the blue line starts to match up with the red line. So it's kind of like they're being buddies together here until this minimum value, and then whoops, the green line's moving off. Now, notice what I did here. I paused it using my enter key. So if you catch it in time, you can stop and talk about different features. All right. So when I go to, maybe I should have really, before I started even talking about this, maybe I kind of jumped the gun here. I should have had, let's shut these equations off. This is really easy to do. Once you have them typed in, you just put your cursor on top of the equal signs and hit enter, and that will shut them off, but they're still there so you can look at them. If I graph that absolute value, notice we have the V that we expect. It should appear to be a little bit more of a vertical stretch, more of a narrow opening here of that V. That square window, that decimal window, does help out on showing that. But I have a minimum value here. That minimum value, it's really helpful to identify. And if I go and hit trace, this is the nice thing about that zoom decimal, is the tracing goes in decimal form, goes up by a tenth because I have it set up to that default. And if I look over here, when y is equal to 0, I have that minimum value when x is equal to negative 1.5. I like using minimum value as that terminology there. Again, that's my personal preference, because when I teach calculus, we talk a lot about minimum values and maximum values, and it starts to get students to kind of recognize that terminology that they will be hopefully using later in the calculus class. Okay, so there is our minimum value of negative 1.5. So when I go back to this, and again, I probably should have graphed that before I put in these two equivalent expressions, is I'm going to hit graph. Once again, boom. Yes, I'm looking at where these two are. Boom, right there. They're all three working. They're all three equivalent right there as that minimum value, okay? So then I'm hitting enter. All right, so let's look at this. We need to restrict this domain. So when I go to restrict this domain, I'm going to really look at a piecewise graph. So I'm going to come down here, and I'm going to shut this off, and I'm going to shut this off. Okay, piecewise graph. So let's take this absolute value, and let's talk about this piecewise. Where can we find it? I'm going to hit math, and I'm going to arrow up. Letter B is piecewise, in case you didn't know that was there. And you can go up to 5 pieces on the 84. I'm going to just use 2. And then I'm going to go to and type in the 2 equivalent expressions that I have here. Now, remember the 2x plus 3, that was working. That was my red line. That was only working after my minimum value. So I'm going to hit when x is, okay, now I got to get that test button up again. Second, math is my test button. when x is greater than or equal to, what was that, negative 1.5, I can use the decimal form. It really doesn't matter. And then I have the opposite of 2x plus 3. And that was happening, that was true when x was less than that minimum value. So I'm going to have x is less than is number 5. Now remember, you can use a fraction here, alpha x, for that negative 3 over 2. So, you know, decimals or fractions, it doesn't matter. So then getting students to understand that when we do this equivalent expression, we need to have that domain restriction. So then when we put this in, we can see that our piecewise, which is in magenta, is working, okay? All right, so those two are equivalent. That is everything I have on the 84. So if I want to switch over to the Nspire here, I'm doing this. Okay, so I always tell my calculus students, I always have to train them, or even students in pre-calculus when using your calculator for an exam. I don't like working in Scratchpad. I like keeping record. What if I want to go back and review? I like to start a new problem. So I'm going to hit Doc and see number 4, Insert. I'm going to insert number 1, a new problem. So I start up there and I'm going to add a graphs page. Now I'm starting with 2.1, which means all my variables are kind of reset. They're kind of going back to the original, and they will not talk to the functions in 1.1. Variables do not transfer over into problems. Okay, so this is very similar. We're just going to find the absolute value. So making you aware of this on the Nspire, we hit our template key over here by the number 9, arrow to the right. Oops, went too far. There's my absolute value. And I hit my 2x plus 3. And I can graph that, all right? And now we couldn't go through the same discovery of type it in the 2 pieces, but to save time here, because I think Dennis has another portion to come back to, I'm just going to demonstrate, I hit tab. Where is the piecewise in the Nspire? Well, again, didn't we see that over there on the template? Yes. Where? There it is. So it's on the left. I need 2 pieces. And again, I would type my 2x plus 3, where x is greater than or equal to negative 1.5. Now my greater than or equal to is a control equal. And then I have, there we go. And I'm just going to type in my negative 1.5. And then I have the opposite of 2x plus 3. And that would be when x was less than 1.5. And there we go, my less than. And if I go to graph this, there we go. And I could, again, do my favorite menu, and then number 5, trace all, or trace, and then number 2, trace all. Again, we can also be using tables to look at values. That is an option as well. Now, when I look at this, just kind of finishing this up, we now can go back and say, oh, wait a minute, we weren't quite correct on this. We need to put in, for our equivalent expressions, our domain restrictions. So up here, when I am working with just u, the absolute value of u, I would go back and say, we should have put u greater than or equal to 0, and when u is less than 0, okay? So, goodness, if you pin on. Okay, in calculus, where is this going to be helpful? Looking at absolute values in a limit here, students kind of freeze up. Like, what do I do with that absolute value? So hopefully if they've been introduced and kind of reviewed the concept of writing an absolute value as a piecewise function with a domain restriction, they could look and say, well, as x is approaching -3/2 from the left, I would be using this restricted domain. So in the numerator, instead of that absolute value, I'm going to step in and just put in the opposite of 2x plus 3 in the numerator, which we see it reduces down to -1, and the limit of -1 is -1. All right. I am looking at the time, and Dennis, did you want to work a little bit with
Yes, that would be great.
With your, okay, I'm going to pass the ball over to you now. And you should have it.
Okay. So one of the things that is most annoying in my time as an AP reader is when students do good calculus work but lose credit for poor algebra or poor notation. Communication and notation is a huge skill starting in Algebra 1 that teachers should model so students follow. And to use precise mathematical notation is important. And so I want to give you perhaps a sample free response question. Okay, perhaps a student is given this function f of x and asked to find f prime of 1, and it might even be stated find the slope of the function, slope of the line tangent to the function at x equals 1. And there have been many questions like this before on FRQs, and it's usually given 2 points. 1 point for the derivative of the function, and then 1 point for the answer. So let me show you a typical student response. Here, the student does f prime of x, and appropriately uses the chain rule to get 8 times the quantity 3x squared plus 5x minus 2 times the quantity 6x plus 5. And then the student has the correct answer, 528. So the student gets 2 points for both the derivative and the answer. But unfortunately here, the student also loses a point because they've done a mistake that we call linkage error. This arithmetic expression is linked improperly to the value of the derivative. And so the student got both points, but if we see a linkage error, we take a point away off of the answer. And so even though the student had good calculus, his notation cost him. So here might be a more appropriate way. The student could write f prime of x and show what its value is, and then on the next line do f prime of 1. Stephen Davis, who has been the chief reader for the past 4 years, always tells us that the equation sign is a verb, not punctuation. And unfortunately, students use the equation equal sign as a comma, and their math work is one big run-on. Students need to learn that when they've finished a thought, they need to go on to the next thought and not to connect two different non-equivalent expressions with equal sign. One other note about a reader, as being a reader, another annoying thing is deducting points for arithmetic errors. If a student were to have continued this arithmetic expression and gotten something other than 528, even though they did all the calculus right, they spent time doing arithmetic and then lost the point on the answer if they were to get any other value. So students should be encouraged not to simplify arithmetic expressions, but once they have their value of x substituted in, to go ahead and get the points there. So one place that I like to emphasize precise notation is when I teach rational expressions. So f of x is equal to 2x minus 8 over x minus 4. And what I'd like to do really quickly is show how I like to connect this idea of the rational expression to a ratio table on using a new feature on the Nspire. So I'm just going to start in a new document and open up a graphs page. And what I'm going to do is I'm going to graph the numerator, 2x minus 8, the denominator, x minus 4, and then I'm going to change my window. I like on the Nspire that I can come over here and actually click on those n values of the axis and change them. So I'm just going to go from -1. I will leave the y values alone, and I'm just pressing tab to move between. And I'll go from -1 to 11. And a new feature on the CX2 is called path plot. You can find it menu, trace, path plot, And the first thing I'm going to do under path plot is setup. I'm going to set the path step to 1 so that it only finds the integer values of x as I do this path plot. Path plot is reminiscent to graphing on the parametrics on the 84. The functions used to graph nice and slowly, and you could kind of see it develop. And with the Nspire, the graph kind of just magically appeared. And so path plot gives us a chance to slow it down and to do it step by step. So I'm going to path plot the function, and it's very much like the trace feature, except I get to watch the graph get plotted as I move forward pressing the arrow keys. So I'm just pressing the right arrow key, and we can see the values of the numerator and the denominator. And what students can see then is -6 and -3, -4 and -2, -2, -1. And what I want my students to do is just to collect information so they can come back and create a ratio table, very much like they would have done when they were dealing with equivalent equivalent ratios when they were doing arithmetic. And they can see that these ratios are equivalent and have a common ratio of 2. But as we plot, my students hopefully will see that we run into trouble when we get to 0. We can't divide by 0, and that is undefined. This is an important idea, in calculus, because students might write 2x minus 8 divided by x minus 4 is equal to 2. But that's not being precise. This is an opposite situation where this is true for all values of x but 1. And as Jan showed us, we could actually graph this as a piecewise function, 2, comma, x not equal to 4. This expression is now equivalent. When students move on to calculus, this problem is solved because the limit doesn't care about the value of 4, and it protects us with our equality. As we run out of time, I suggest those of you who use the 84 try to explore this same ratio table idea using the table feature, but set your dependent feature to ask. We have some great files in the downloads that you can go to where we built some functions, some TNS files where you can explore linear equations by changing values, and we have some graphical database files of these rational expressions explored with a table. At this time, I'm going to turn it back over to Mike, I think, if I can. Mike, you there? Okay,
Yep.
I've got it. All right, stop sharing. I'm going to turn it back over to you.
Got
Sorry.
it. No, we're good.
Okay.
We're good, Dennis. Thank you.
Thank you.
As we begin to wrap things up tonight, if you have any last-minute questions for Dennis or Janice, please try to get those asked. I know they'll do their best to get those questions answered. One thing I want to show is we currently have an extra credit contest that started, I think, a couple weeks ago. And it's pretty simple. It allows you to win prizes based on earning points, and you can earn points by doing lots of different things, one of which is attending a webinar like tonight. So feel free to visit our website and check out the extra credit contest. You can register if you want to earn points for tonight's webinar through the extra credit contest. You're going to need a special code. It's not case sensitive, and tonight's special code is all one word, is build foundations. I'll put that in the chat window. Again, that's build foundations. Not case sensitive. As Dennis mentioned earlier tonight, we're excited that the T-Cubed International Conference is coming to Dallas this coming March, which will be here before we know it. It's a great place to connect with other educators, learn a little more about technology and pedagogy and content, and we hope to see everyone at the conference. If you go visit our website, there's right now a discount based on your early bird registration. So feel free to visit our website to learn a little more. And tonight we're also giving away to one lucky winner a registration. So tonight's lucky winner is Leslie Whaley. So Leslie, congratulations. We hope to see you as well as everyone else at the T-Cubed International Conference. To receive a certificate of attendance, go ahead and click the link in the chat window. Also listed as a link for the documents from tonight from Janice and Dennis. If you miss these links for any reason, you should be getting a follow-up email in a couple days, and that follow-up email will include links for the certificate, the documents, and the recording. And if you're watching this on demand, go ahead and copy that link into your favorite browser to receive your certificate. Thanks so much, Dennis and Janice, for everything you shared tonight. Definitely gave me a lot to think about talking about expressions and equations with my students. I really appreciate it.
You're so welcome. Thanks for everybody showing up tonight.
Yeah.
I agree.
You,
second that. Thanks, everyone, for joining us. And we hope to see you back online real soon. Have a great night.